In the next, we consider to evaluate the difference between two functions, that is, the target function and our hypothesis over the data space with respect to some distribution. We want to measure the difference, that is, the areas that is enclosed by the difference between two function curves over the entire X space. Let's review a little bit. We cannot directly compute this integral because, for one thing, we don't know the target function fx. For the second thing, we don't know the data distribution. So the integral is not computable. What is available to us is we can compute the difference between the given value of the desired target function and the prediction by some hypothesis over given training examples. So we can compute the empirical estimation of the overall error measurement. Let us introduce some denotations for the convenience of discussion. We will call this estimation of the loss as in-sample error. That is the overall error measured within the training data set, the training samples, in-sample error of a hypothesis, some hypothesis H. And we will call this notion the integration over unknown data distribution and computing the difference between the hypothesis and the unknown target function as out of sample error. The ultimate goal of learning is to optimize over a hypothesis family. We want to find some H that minimizes the out of sample error, E out. But we only have access to the in sample error, E in. And the hope is these two kinds of errors are linked to each other. Note that we introduce a symbol, this capital D, that represents with a slight abuse of the sample. It represents the training samples in dataset follows an independent distribution of the data in the X space. To illustrate the difference between E in and E out and how they are linked to each other, let us have a very specific example. We have a concrete example using programming language. Let's implement our example as follows. Here I prepare the environment like this. I have a numpy and some plotting function here. This is a random sample generator. For example, let us have the data distributed from 0 to 1, evenly distributed. We have the even distribution, uniform distribution between 0 and 1 of data. Let's mark it here, and let us consider our target function to be some very simple one. It returns true when x is greater than 0.5, otherwise it returns 0. as simple as this. This is our target function. And let's define any hypothesis. For example, this hypothesis is our hypothesis for test. It is not exactly the same as our target function because we are simulating the situation that we don't know our function, our target function, and we only have access to some training samples. Now we will make a guess about the target function. Let's see, it returns true when x is greater than 0.3. Then, in this particular case, excuse me, we know the the out of sample error is exactly 0.2. If we call each misclassification has a cost of 1, because x is distributed evenly from between 0 and 1, we will have a chance of 0.2, that is when x is between 0.3 and 0.5. H will not agree with f, and for other x, h and f will agree with each other. So the oracle out of sample error is 0.2. Now let us simulate the situation where we do not have this oracle value of the out sample error. We can only evaluate our h using some random data samples. Let's do this experiment for multiple times, but let's now simulate one experiment. Let's say we will have 10 samples in our training data. This rand function is the desired one. It will generate random samples uniformly distributed from 0 to 1. So we will have this number of training samples, and the in sample error will be the total number of samples on which fx disagrees with hx. This is divided by the sample number. Let's print out the result. See, fx and hx, and in to have some sanity check. Okay, they agree mostly, but with one example they don't agree. Let's see what is this example. Okay, this falls exactly between 0.3 and 0.5. What we will do is we will repeat this experiment for multiple times and record all the outcomes. See. In sample errors, we prepare an empty list to record all the experiment results. Let's do 10,000 experiments. For each experiment, we calculate this number and we let in sample errors record use append function of a list to record this in-sample error. So let's have a look of the distribution of the in-sample errors. We plot the histogram of in-sample errors. Here is what we get. So we evaluate the in-sample errors on the training data, and we realize that it is possible that the in-sample errors differs from the out-sample errors. And in our example, in 10,000 experiments, we have a distribution like that. We know for true that the oracle out-sample error in this example is 0.2. And the in-sample error we got has this distribution. We see for most of the cases, it agrees closely with the out-of-sample error. Ignore this gap. It's because we haven't put much attention on how the histogram has been drawn. The 0.1, 0.3, and 0.2 took the vast majority of all the experiments. But there are in some of the experiments, just because of the pure bad luck, we end up with a very large difference between the in-sample error and the out-of-sample error. Okay, bear this in mind. We will consider this aspect of learning again and again in the machine learning subject. So, for summary, for learning to make sense, we need two aspects. First one is the in-sample errors. This only error that is available to us, that has been evaluated on the given training sample, needs to be useful. It needs to track the out-of-sample error. Second, in the hypothesis family, we will be able to select some hypotheses to minimize the in-sample errors. So we need to minimize this guy and drive the two close to 0. When we drive this guy close to 0 and we have some kind of guarantee that this guy is close to this guy, we actually hope that the out-of-sample error of H is close to 0. And according to this measurement, this picture, we will see, okay, when the out-of-sample error of H is close to 0, H is close to the target function f. So that are two pieces, twofold of meaning of machine learning.